So in this video I'm going to discuss the questions and solution in thermal and statistical physics which appeared in JEST 2019 examination. So let's take a look at the first problem. The statement is, consider a system of n distinguishable particles with 2 energy level for each particle. Okay, so we are having a system of n distinguishable particles. So total number of distinguishable particle equal to n. Okay, and with 2 energy level for each particle. So that means each particle can access 2 energy levels. Okay, a ground state with 0 energy, a ground state with 0 energy, and an excited state with energy E which is greater than 0. Okay, what is the average energy per particle as the system temperature T goes to infinity? So we have to evaluate the average energy per particle when T goes to infinity, or when temperature approaches a very large value. So we can solve this problem by making use of the partition function approach. So for that purpose we will simply obtain the partition function for one single particle. Okay, so for a single particle the partition function reads q1 and then gi exponential minus beta ei. Okay, now because nothing is mentioned about the degeneracy, so we can take it to be unity. So that means we are considering the energy level to be non-degenerate. Okay, so the corresponding partition function for one single object will be exponential minus beta, and then the energy ground state energy, that's 0, plus exponential minus beta e. So this is 1 plus exponential minus beta e. Okay, because particles are distinguishable, so we can immediately write the expression for the n particle partition function q1, that is equal to q1 power n, or that is equal to 1 plus exponential minus beta e and its power n. Okay, now we want to obtain the expression for the average energy. Okay, so the average energy for a system of n particle is given by u, that is equal to minus curly beta of ln qn, and that is equal to minus curly beta of ln 1 plus exponential minus beta e and its power n. Okay, and it comes out to be equal to u, that's the total average energy of n particles, that is equal to minus n, and then differential of the logarithmic term which is 1 upon 1 plus exponential minus beta e, and then again differential of the exponential term with respect to beta, so that will gives us a term exponential minus beta e, and then again another differential with respect to beta, that will give us a minus e. Okay, so therefore the average energy that comes out to be equal to minus will become plus n e. So I'm taking this exponential function into a denominator, so it comes out to be equal to exponential beta e plus 1. Okay, so that means this is the average energy for n particles. So average energy per particle, that is u divided by n, that is equal to e upon I'm writing one at the first place, 1 plus exponential beta e, which is e upon kt. That's the average energy per particle. That's a general expression basically. So let me call this as equation 2. But now we have to obtain the average energy per particle as t goes to infinity. So as t goes to infinity, the exponent in the exponential term, that is e by kt, in this condition that will approach to a 0 value. So therefore the average energy per particle, it turns out to be equal to, it's approximately e upon 1 plus exponential 0, 1 plus e power 0, that is e divided by 2. Okay, so therefore B is the correct option here. So we can continue with the next problem. So we are given a situation where a diatomic molecule with molecule with an infinite number of equally spaced non-degenerate energy level. Okay, so we are having a diatomic molecule with the equally spaced non-degenerate energy level. So we are given a situation where the energy levels, they are equally spaced. The spacing between any two adjacent level is E. So that means this is E, this is also E. Okay, and the ground state energy is 0. It's given that the ground state energy is 0. So this is E, this is 2E, and the next level will have energy of 3E, because it's given that separation between successive energy level, that is E, and so on. Okay, what is a single particle partition function? Okay, so and also it's given that the all energy states, they are having a degeneracy of unity. These are non-degenerate energy state. Okay, so it's easy to write the partition function for such a situation where the energy states, they are non-degenerate. So the partition function for one single object Z1, that is equal to summation gi exponential minus beta ei, where I, it's running from 1 to infinity, and gi, it is 1 for all the energy states. Okay, so therefore for the first energy level, the corresponding contribution to the partition function will be exponential minus beta multiplied by energy, which is 0. So that will give us a 1. For the second energy level, the term will be exponential minus beta e, and for the successive exponential minus 2 beta e plus exponential minus 3 beta e plus 1. Okay, and we can rewrite this as, because this is equal to a series with infinite terms in the series and the addition. So with the first term as a, which is equal to 1, and the common ratio as exponential minus beta e. So this is, its sum is equal to a upon 1 minus exponential minus beta e. Okay, so if we just take a look at the results, I mean the options that are given to us, 1 upon 1 minus exponential minus beta e. So the B part, it's containing a positive sign. So that means it doesn't match with our result. Okay, and then okay, this is also not correct. C is also not correct, and D is also not correct. So that means here none of the option is matching our result. Okay, so but this is the final result. So the conclusion is that none of the given options match the result. So let's take a look at the next problem. The statement is, consider a grand ensemble of a system of one-dimensional non-interacting classical harmonic oscillators, each of frequency omega. Which one of the following equation is correct? Here the angular bracket indicate the ensemble average. N, E and T represent the number of particle, energy and temperature respectively. Kb is the Boltzmann constant. So we are given a one-dimensional ensemble of harmonic oscillator, one-dimensional harmonic oscillator system. Okay, so in grand canonical ensemble, we notice that it's the number of particles and the energy. Both of these two, they are considered as variable. Okay, so in one particular energy state, you can say the average number, we may assume it's not going to be n. Okay, it's going to be, basically it's going to be some average quantity. So because it's a variable, it will keep on always changing, so we talk about the average number rather than the absolute value. Okay, now for a 1D harmonic oscillator, the relevant Hamiltonian for this system is given as p square, because it's a one-dimensional harmonic oscillator. P is x square upon 2m plus 1 by 2 k x square, where k it's the spring constant, or it also represents the physically, it also represents the bond strength. Okay, so that means if we talk about the average energy per oscillator, so average energy per oscillator, per harmonic oscillator, so we are having two square energy terms. So from the equipartition theorem, first square energy term, it will contribute it will contribute kT by 2 to the average energy, and the second square energy term will also contribute kT by 2 to the average energy. So the total average energy per harmonic oscillator in one dimension will be kT. But now we are talking about the ensemble average. So that means the average energy, so that is equal to, it's basically the average number of particle and then multiply by the average energy per oscillator. Okay, so therefore the correct option here, it is the option D. So let's take a look at the next problem also. The statement is, consider a non-relativistic two-dimensional gas of n electrons with Fermi energy EF. Okay, what is the average energy per particle at absolute zero? So that means when we are talking about a system at absolute zero, so that means we are talking about a degenerate case, perfectly degenerate case of the electron gas. So it's a T is equal to 0 Kelvin. So that means we are talking about degenerate electron gas. Okay, now in order to calculate the average energy per particle, first of all we must have an idea about the density of states in a energy range from E to E plus D. So because the particles or the electrons, they are fermion and they are non-relativistic particle. So for non-relativistic particles, the energy and momentum relationship is given by E, that is equal to p square by 2m, where p square is equal to px square plus py square. It's in two dimension because, okay, so here the number of states in with momentum less than equal to p, okay, that is equal to the available phase space volume, that is the area, or in two dimension. See, we are talking about the Fermi gas in two dimensions. So okay, so that's why we are talking about the area, okay, in the ordinary space, and then multiply by the area available in the momentum space, that is pi p square divided by the cell volume or the cell area in two dimension, which is h square. So with the help of this expression, we can write the expression for the states, the density of states with energy less than equal to E, and that is equal to so here I'm multiplying with GS, so that's a spin degeneracy factor. Okay, this is spin degeneracy factor. In principle, we must also multiply here. Okay, and for the electron, it is 2s plus 1, that will give you a factor of 2 here, GS, and then pi a upon h square, and then multiply by p square. So p square is equal to 2me from here, so I'm replacing it with 2me. Okay, so that omega e, it turns out to be equal to 4 pi m a upon h square multiplied by E. So from here we can immediately calculate the density of states in the energy range E to E plus dE, that's omega dash E, which is equal to d omega E upon dE multiplied by dE. Okay, and that is equal to omega dash E, which is nothing but GE dE, that's the density of states in the energy range E to E plus dE. That's what we are looking for. Okay, so this is equal to, so we have to differentiate this expression with respect to E. So ultimately we are left with this quantity. Density of states in two dimensions is going to be independent of energy, so that is 4 pi m a upon h square dE. Okay, so let's call this as our equation 1. So now we have to determine the average energy per particle, and that can be calculated as follows. So the average energy, that's average energy per particle, that divided by total number of particle, and that is equal to the, now we have to calculate the average energy from 0 to EF, because we are talking about a system at absolute 0, and at absolute 0 only the states up to the Fermi level they will be occupied. So all other states above the Fermi level they will be empty. So that's why we are making calculation only up to the Fermi level. So the average energy, this is the energy, and then the probability distribution function, or the Fermi-Dirac probability distribution function, because we are talking about the fermions, that's why we are multiplying here with the Fermi-Dirac probability distribution function, and then the density of states, G E D E. Okay, and then divided by the number of particles. So number of particles is given by the expression 0 to, again the calculation is only up to the Fermi level, and then probability distribution function f of E multiplied by the density of state. So that will give us the total number of particles in principle. Okay, now what is Fe? So let's call this as equation 2. Fe, it refers to the Fermi-Dirac probability distribution function. This is equal to 1 over 1 plus exponential E minus EF upon KT. Okay, so now this function has special property at absolute 0, and if we just make a plot between the probability distribution function f of E as a function of energy, now at absolute 0 this function, it looks like this. It's like a step function. Okay, so at EF, E is equal to EF, when we substitute here E is equal to EF, it is E power 0 by KT, that is f of E, it will become 1 by 2. So at E is equal to EF, the behavior of this function below the Fermi energy, it acquires a value of unity, and for any energy greater than EF, it is going to be equal to 0. Okay, so that's why in this expression, because we are doing the calculation of the integration only up to the Fermi energy, because beyond the Fermi energy value EF, this function is taking a value of 0. Okay, so when we will substitute here the value of 0, f of E equal to 0, so this integral will vanish. Okay, so we are going to substitute f of E equal to unity in both of in numerator as well as in the denominator. Okay, so now they will substitute the value of GEDE from equation 1 in equation 2, so that energy, the average energy per particle, it turns out to be equal to 0 to EF, and then 4 pi MA upon H square, and then E dE. Okay, divided by 0 to EF, and then again the constant term 4 pi MA upon H square dE. So this is a constant term, this is also constant term, they will cancel with each other, and ultimately upon integration we will obtain, this is equal to, in the numerator we will obtain EF square by 2, and in the denominator we will obtain EF. So EF and EF, they will cancel with each other, so that the average energy per particle in two-dimensional non-relativistic system, this is EF by 2. So therefore option C is the correct one here. So let's continue with the next problem. The statement is the energy spectrum of a particle consists of 4 states with energies 0, E, 2E and 3E. Let ZBT and ZFT and ZCT denote the canonical partition function for 4 non-interacting particles at temperature T. The subscripts B, F and C denotes corresponds to boson, fermion and distinguishable classical particles respectively. Let Y is equal to exponential minus E by KT. Which one of the following statement is true about ZB, ZF and ZC? Okay, so basically we have to determine the partition function first, and then the degree of the corresponding polynomial, that in terms of which a partition function can be written. So we will I'm going to explain it with the help of one partition function for the system of boson, and then we will generalize this result for the rest of the two cases. Okay, so let's try to understand this problem. Basically we need not to determine the entire partition function here. Simply we have to recognize the maximum power in the partition function, maximum power of y, which is exponential minus ey kt. Okay, so the if you just take a look at the the statement, so we are having a system of 4 energy levels. Okay, so for boson, the maximum degree in the partition function that's obtained when all the particles they are lying in a the energy states with the largest energy. Okay, so here these states they are having energy 0, E, 2E and 3E. Okay, so here if all the particles they are lying in the ground state, that's the first case, and if they are lying in the first excited state or the second excited state, or the another option could be that because they are bosons, so they all of them they can stay together in one energy state. Okay, and similarly there are additional large number of possibilities where you can imagine one particle in one energy state and distribute other by following the different kinds of distribution. So you can put 1, 2, 3 or 4 particles in a single energy state, so that will give rise to a large number of terms. But we are only interested in the term in the partition function having largest degree, and that will be obtained for the case when all the particles or the boson they are lying in the highest energy state, which is 3e here for the given description of the problem. Okay, so here for example for this microstates the corresponding energy will be 0, and here when all 4 particles they are lying in the energy state E, the energy will be 4e, because 4 particle at energy state E they will have energy of 4e. 4 particle in energy state 2e, so they will have energy of 8e, and here 4 particle in energy state 3e they will have a total energy of 12e. Okay, so now if we write the partition function, but please note that these are not only the 4 microstates which this system of 4 boson in these 4 energy states can have. They are going to a large number of microstates, but the only point is that we have to identify the microstates with the largest energy, and that's going to 12e in this case. Okay, so the corresponding partition function, if you start writing all the terms in the partition function for system of boson, we are having 4 boson. Okay, so the partition function will look like this. Okay, the first term I'm writing for this microstate, so exponential minus beta into E, energy E is equal to 12E here, so minus 12E upon kT plus, now for this exponential minus 8E upon kT plus exponential minus 4 E upon kt plus 1 plus so on plus remaining terms. Okay, but we notice that it's the highest, the occupancy of the particle in the highest energy states that's giving the largest value to the exponent. Okay, so this can be written as exponential minus ey kt power 12 plus exponential minus ey kt power 8 plus so on, or this is equal to by power 12 plus by power 8 plus so on. So that means here for the case of bosonic system, degree of the polynomial is 12. Okay, the same way for the classical system also. For classical system, because in case of classical particle there is no condition on the occupancy of the particle, so that means all the particles they can stay together in a single energy state. So for classical particles, okay, so Z classical will look like this: ZC, that is equal to by power 12 plus by power 8 plus so on. So that means here also degree for the partition function, the degree will be 12. Now in case of fermion, we just take a look at the the condition that the fermion need to satisfy, that we cannot put more than one fermion in one single particle state. That means we can put only one fermion in a single particle state. Okay, so 0 E 2e and 3e. So here energy, this is the only one microstates these fermion can access. Okay, so here the total energy of the system is E, that is equal to 6 times E, so that Z fermion will be exponential minus 6 E upon kT, or that is equal to by power 6, so that degree is 6 here. So therefore the correct answer is for Z boson and Z fermion and Z classical, they will have degree of 12, 6 and 12 respectively. So that means 12, 6 and 12, therefore option A is the correct one here. Let's take a look at the final problem. The statement is a diatomic ideal gas at room temperature is expanded at constant pressure. Okay, so we are having ideal diatomic gas and it's expanded at constant pressure P. Okay, if heat absorbed by the gas is Q is equal to 14 joule, so that means delta Q P, it's a process is taking place at constant pressure, that is equal to 14 joule, it's given. Okay, but it's the maximum work in joule that can be extracted from the system. So the maximum work that can be calculated with the help of the first law of thermodynamics, which says that delta U is equal to delta Q minus W. Okay, so from here one can calculate work done during this process, constant pressure process, W, that is equal to delta Q minus delta U. Remember that delta Q, it's it is at constant pressure at fixed P, it's given to us. Okay, let's call this as equation 1 and this as equation 2. Okay, so now we know that QP, or the delta QP, it is equal to Cp delta T in the constant pressure process. Okay, and this is given to be equal to 14 joule. Okay, now if we substitute the value of Cp now for the diatomic gas here, so let's note that Cb, that is equal to diatomic gas will have a 5 degrees of freedom, 3 translation degrees of freedom and 2 rotational degrees of freedom at ordinary temperature. So we will have 5/2 R per mole and Cp will be 7/2 R per mole. Okay, so Cp delta T, so Cp delta T mean it is 7/2 R delta T. Okay, and from here we can calculate the value of delta T that will be helpful for us to evaluate delta U. So delta T from here, this is equal to 14 into 2 divided by 7 R, and this is equal to 28/7, that is 4 upon 8.314. Okay, and this is approximately equal to 0.481 degrees Celsius, because it's a difference delta T. Okay, it doesn't matter whether we are taking difference in Kelvin or Celsius, it's going to be same number. Okay, so now delta U that is equal to Cb delta T. Okay, because we are taking 1 mole here, so per mole we are doing the calculation, so that's why N will be unity here, Cv delta T. So Cv is equal to 5/2 R, 5/2 into R, and then multiply by delta T, and that is equal to 5/2 into 8. That's the value of the this gas constant 8.314 multiplied by delta T, which is 0.481. Okay, so delta U, it comes out to be equal to 9.99 joule. Okay, so now we are having both of the quantities to calculate the value of W. So W is, it is 9.997. Basically it's 10 joule approximately. So W is equal to delta Q minus delta U. So delta Q is given to be 14 joule minus delta U, we just evaluated, it is 9.997. So ultimately this is approximately equal to 4 joule. So therefore 4 joule is the right answer.